Hi everyone. In this video we're going to talk a little bit about action potentials, and we're going to focus in this video about the ionic basis for action potentials and how they work. So we're going to be going into a little bit of detail. So if you aren't comfortable with terms like equilibrium potential, resting membrane potential, ion channels, I would recommend that you review them from another resource, simply because they are quite an expansive topic and it's difficult to cover them within one 10-minute video. So just a quick definition, an action potential is a change of the membrane potential of a neuron from negative to positive to negative again that allows for the propagation of an electrical impulse. And so we're going to talk about how ion channels and the flow of ions contribute to making this process work. So let's look at this first. Alright, so just to give you a quick glimpse of what we're looking at, this is the cell, and what I've done is I've just taken a chunk of it, and that's what we're looking at right now. Now, you'll remember from your resting membrane potential knowledge that the concentration of ions is very important to understanding how membrane potentials are formed. And when talking about action potentials, we're really only concerned about two ions. We're concerned about potassium and sodium. And what I'm doing here is I'm just making one side obviously bigger than the other to show where the concentration is more. So you can see that potassium is concentrated much more inside the cell than outside, and sodium is a lot more outside than it is inside. Now, we understand from basic biology that ions want to flow from high concentration to low, so we know that there is a desire for these ions to flow down their gradient. Now, what controls whether they do or not? And that's the essential concept behind how action potentials work, and that's the idea of permeability. And when we talk about permeability, what we're referring to is how many channels of what type are open at a specific time. And changing the permeability will change the amount of an ion flowing at a given point. So for example, during the resting state, there are not as many sodium channels open as there are potassium channels. So potassium is allowed to flow down its gradient, and that allows for it to establish the resting membrane potential at negative 70 millivolts. So I'm going to jump in straight to looking at this graph. Now, this is a graph of an action potential. Now, what I'm going to try to help you do is help understand how the structural portions of it, the ion channels, contribute to the different phases of the graph, because sometimes it's kind of daunting to look at the graph in isolation. It's a little bit easier to look at these side by side. And before we delve into this discussion any further, I wanted to clarify a couple of terms. So if we were at a given given potential, let's say whatever this is, and we go more negative, the term for that is hyperpolarization. Becoming more negative is called hyperpolarizing. Now, it doesn't matter if you're starting from somewhere down here, or even if you're in the positive region becoming more negative, the act of becoming more negative is hyperpolarizing. Now, the opposite, becoming more positive, starting from a really negative number, or even starting up here, moving up, is called depolarization. Now, these are important concepts to understand because I will be using them freely when talking about the action potential. So understand that hyperpolarization is negative, or moving negative. Depolarization is moving positive. So now that we understand those concepts a little bit better, let's look at the phases of the action potential. And so what I'm going to try to do is make that connection between the different phases of the action potential to the ion channels that you see here. So here we can see that we're at negative 70 millivolts. That's the resting state. And we know that the channel most responsible for the resting state is the potassium channel. So in this case, the membrane is very permeable to potassium, much more than it is to sodium. So when I do this, I mean potassium is, the permeability is much greater than it is for sodium. So we know that potassium is very easily flowing down its gradient. Now, an interesting concept behind the action potential is the way the membrane potential depolarizes is through the application of a stimulus. A stimulus usually makes the action potential become more, or the membrane potential become more positive. Now, if you, let's say, apply a stimulus to this point, and you get to negative 60 millivolts, and then you stop applying the stimulus, there's nothing stimulating the neuron anymore. the membrane potential will actually just drop back down to its resting potential. Nothing will happen. Now, if you stimulate it to a certain point, which in the case of neurons is negative 45 millivolts, if you take it to this point, the entire action potential will happen without needing any more stimulus. So basically what this states is there is a certain amount of stimulus required for an action potential to happen. And once it reaches this point, the rest of the stages of the action potential will follow, but if it doesn't reach this point, the other portions will not follow. This is called the all or none property of action potentials and is very important to understanding how the action potential works. So let's take a look at the next phase of it. So when we reach this point, let's say we've applied sufficient stimulus, what's going to happen now is we have to somehow account for this sudden depolarization. You can see that this is depolarization, correct? It is becoming very positive. Now the way this happens, I'm going to call this the second phase. The way this happens is we're relying on a new player in this game. This is the voltage-gated sodium channel. Now what happens is once we reach this voltage of negative 45 millivolts, it causes this channel, which is normally closed at rest, to open up. Now you'll remember that sodium is a lot more outside than inside, so it wants to take its positive charge inside, but we don't have that many channels open. But once you get to negative 45, you open this guy up, which makes sodium very happy. And sodium can suddenly flow down in a huge amount into the cell, making the inside of the cell very, very positive. And this happens very quickly. It's a very rapid depolarization phase. So during this phase, the permeability to sodium is much more than potassium, and you'll see the permeability changing. Here in the resting state, potassium is more, and here sodium is more. Now after it reaches a certain point, about 30 millivolts, and this is positive 30, at this point, the voltage-gated sodium channels will start closing. Now, one thing I should clarify, it's called voltage-gated because they open at a specific voltage. They open at negative 45 millivolts, and that means they also close at a certain voltage as well. So they begin closing around this point. And as they start closing, they kind of curb off the positive movement of the action potential. And at this point, and this is when our next player comes in, the voltage-gated potassium channels. Once again, voltage-gated because it opens at a certain point. Now when this opens, you'll have to remember that up until this point, this entire rapid depolarization phase, the flow of sodium inwards was overshadowing the flow of potassium outwards, which is why there was so much positive moving in, and it really didn't matter how much positive was moving out. Now at this point though, this has already started to close, okay? And we're suddenly opening this voltage-gated potassium channel. Now the potassium ions have another conduit for leaving, so they're very happy now, and they start flowing out, and they start taking their positive charge out of the cell. And so that leaves a negative charge inside, and that is responsible for this phase. So we have the voltage-gated potassium channels, sodium channels closed, and the potassium are open, causing this rapid hyperpolarization phase. Now, this hyperpolarization is not as fast as the depolarization phase, but it still happens relatively quickly and allows for this movement downwards. So during this phase, which I'll call phase 3, the permeability for potassium is way, way more than sodium. So you can see the change, potassium, sodium, potassium again. And then it overshoots a little bit, becomes a little bit more negative than it should, and it eventually ends up right where it belongs, with the beginning state of potassium being more than sodium. So once it reaches this point, the voltage-gated potassium channels are closed. These guys closed a long time ago, and we're back to these two being open. Now, you should know a couple of terms. There is something called the absolute refractory period and the relative refractory period. These are terms that imply that an action potential can only occur after a certain amount of time. Now, these are terms that I think can be delved into in another video, but just know that they exist, that the action potential has a limit to how quickly it can fire. You can't just keep stimulating a neuron, willy-nilly as much as you want. There is a period of recovery. The channels take a certain amount of time to recover. So Once again, these are the basic aspects. Just remember that there are four major players. We have potassium channels, sodium channels, and the voltage-gated potassium, voltage-gated sodium channels that are responsible for the entire movement of the action potential. Thanks.